Hello and welcome to today's webinar, the title of which you can see on the screen. It focuses on combining emerging data collection and modeling strategies in support of signal control optimization. I'm Virginia Sisiopiku. I'm a professor of transportation engineering at the University of Alabama, Birmingham. And I'm here today with my colleague, Mohammed Hadi, from Florida International University to offer you this webinar. Before we get started, I would like to acknowledge our students that contributed to this project that we are describing for you today. And this would be Mohammed Tariq and Rajib Saha from FIU and Gokman Pakhal from UAB. So this webinar is sponsored by the STRIDE Center, and as many of you are familiar, STRIDE is the 2016 US DOT Region 4 University Transportation Center. We are a consortium of universities, 10 universities and colleges in the Southeast, with the University of Florida being the lead institution. And our mission at STRIDE is to develop novel strategies for reducing traffic congestion. As part of this webinar today, I will give you some introduction on our topic, and then we will have two parts. The first part will focus on the survey of practice on traffic signal operations, optimization, maintenance, and management in the Southeast, and I will cover that part as well. And then Dr. Hadi will cover the second part that focuses on methods used for selecting signal timing parameters using data from multiple sources and modeling. While this is going on, we invite you to contribute questions at any time through the chat box, and we will answer these questions at the end of the talk. So the reason that we had the motivation to look at this topic is the fact that considering that urban traffic congestion costs American urban commuters more than 166 billion annually, and more than 5% of this congestion is due to signals. It becomes apparent that if we have effectively designed, operated, and maintained signals, that can be a great thing for reducing congestion and all the adverse impacts of congestion on mobility, fuel consumption, environment, and so on. Another motivation is that in the recent years, we now have emerging data sources including data from connected vehicles that give us new opportunities for improving signal timing and optimization practices. So we find it to be important to explore those ways and try to use these new sources of data as well as new techniques in order to improve signal control as a means of reducing urban congestion. So with these motivations, we defined two major objectives for our study. The first objective was to conduct a comprehensive survey of traffic signal operation, optimization, maintenance, and management practices, focusing in the Southeast US in order to better understand the agency's current practices and needs for the future. And this is important because all the data that we have and all the techniques that we can produce will not be valuable unless the agencies have an interest in using them and adopting them as part of their operations. The second objective that we defined was to propose and evaluate methods and algorithms to combine data collected both from existing as well as new sources with new models and in order to optimize signal operations. we recognize that calibration of traffic simulation model is a critical component of simulation modeling when used to assess or optimize signal timing parameters. And so we put a lot of emphasis on this topic in this part of our work. These objectives were accomplished through a series of tasks that are highlighted here in the scope. We started with documentation of signal optimization and management practices. We did an extensive review on existing and emerging models and data collection methods. We proposed and tested new data and tool integration methods, evaluated those developed methods, and then organized this in a report, a draft of which is now available, and the Stride will make this available in their website late in the summer. So as promised, I will focus on the first part of this work that focuses on the survey of practice in the Southeast. And as usual in the academia, we start with looking at the literature to see what is out there and what we know from earlier studies. What we found is that the first systematic effort to assess the state of traffic signal operation in the US took place in 2005, when the National Transportation Operations Coalition conducted a self-assessment study of agencies that operated traffic signals across the United States. The goal of this work was to bring attention to the state of signal operation, but also to create awareness of the congestion-reducing benefits of good traffic signal operation, and finally to make a strong case for additional investment in signal operations. So that survey, that was the initial baseline survey of 2005, was used to develop the first national traffic signal report card. And there were two more surveys in 2007, 2012 that provided the broad overview of the state of practice in traffic control across the US and Canada. However, from this work and from some other studies that we have identified, we understood that these surveys used aggregated data, and they didn't have any specifics about the geographical areas and how agencies in certain geographical areas operate. And also, one thing that was really missing for a good reason is information about new models and new data that have emerged, including data from connected vehicles that they were not available at the time of these earlier surveys, but now can provide some additional sources that the agencies can use. So in order to address those gaps, we decided to develop a new survey tool and use that in order to collect and document current operating signal retiming and management practices of agencies, specifically in the Southeast, and use then this information in order to understand the reasons behind those choices and identify some opportunities as well as barriers for adopting new approaches, new models, and new data sources into the operations in order to improve the current state of the art. The next slide summarizes the survey methodology. The questionnaire survey that we developed followed the guidelines from IT, Manual of Transportation Engineering Studies, and was developed in the Qualtrics platform. The Qualtrics platform provides some good tools that allowed for both closed-ended and open-ended questions, multiple choice, check boxes, and so on. So it proved to be an efficient way to develop and distribute the survey. As with any survey of this type, we had to go through approvals first to get permission from the Institutional Review Board, the IRB, to disseminate the survey since it involved human factors. So after we cleared the IRB approvals, then we had to identify and contact potential participants. We targeted transportation agencies that operated various sized traffic signal systems in 6 states in the Southeast, and this included Georgia, North Carolina, Tennessee, South Carolina, Alabama, and Florida. And we did that on purpose. So first of all, we wanted to have to document the experience of agencies in the Southeast, since STRIDE is the UTC in the Southeast, but also we wanted to have a variety of agencies involved. So we placed care into soliciting input from jurisdictions of different sizes, ranging from the large ones that we defined as those serving a population of greater than 450,000 people, to medium size, and then finally to small size agencies that served less than 65,000 residents. As far as the survey content is concerned, we included 16 questions that solicited information about the type of agency that we had, the characteristics of the participating agency, their current retiming practices, resources that they used in support of signal control optimization and management, what were their current data collection strategies and future plans for adopting additional options. And finally, we had some questions about the availability of resources. Now, from this effort, we were able to collect 20 detailed responses from representatives of the surveyed transportation agencies. And we went through this closely, and we identified 3 of them that were almost duplicates. So we had to eliminate those. And so we worked with 17 surveys. It may not look like a large number, but still there was a wealth of information in these surveys that we appreciate receiving. And the good thing also was that among those 17, we had 6 from agencies that we classified as large agencies, 6 from medium size agencies, and 5 from small. So we had a very nice representation of the different types of agencies that we have in our geographical region. And overall, these agencies managed more than 9,600 traffic signals collectively. So we aggregated the results by jurisdiction size, and we made sure that, of course, the responses remained anonymous, as we have promised from the beginning. And so today I'm going to share some of these results, and more of those are in our report. As you see here, the responding agencies reported that nearly 74% of their traffic signals that they manage are coordinated, and about 82% are actuated overall, considering all responses. And also from the 17 agencies that surveyed, 14 reported that they have implemented emergency vehicle preemption and 13 special plans for special event management. If you look at table 4, where we summarize the results from a question focusing on how often does the agency retimes traffic signals in their area, we can see that most of the large and mid-sized agencies report retiming their traffic signals every 5 years or more. about 40% and 33% respectively, while the smaller agencies seem to retime them a little bit more frequently, with 50% of them retiming them every 3 to 5 years. Table 5 that you see on the screen summarizes the factors considered by agencies in the Southeast when deciding on retiming traffic signals. As you can see here on the top, the agencies surveyed reported making signal retiming decisions based on review of data and also based on field observations, 24 and 19% respectively. And of course, you know, other factors that contributed to these decisions included feedback from travelers or retiming at certain regular intervals. And about a third of the agencies that we surveyed reported that they combined several of the above mentioned considerations and made their decisions accordingly. We asked specifically about triggers that are used to initiate the retiming process for these agencies. And almost all agencies, 16 out of the 17, reported that their major trigger was changes in traffic demand. Also, many agencies start thinking of retiming those signals when new signals are installed in the area, and geometric changes around you know, the intersections as well as new development in the area also are considered as triggers for checking, you know, the need for retiming signals. Then we asked the agencies to identify sources used in support of signal control optimization and management. And to that question, the majority of agencies reported using national or statewide guidelines for signal optimization and management. And that was consistent between all sizes of agencies. We also seen from their responses that several agencies, about 18%, you know, in total, expressed an interest in developing a set of guidelines for their agency in the future. Furthermore, the survey requested information regarding the current practices with respect to the use of signal optimization software and techniques, and the results are summarized here. It is very clear from these results that the software of choice is Synchro, with 15 agencies out of the 17 reporting using this very heavily for signal optimization. And 10 agencies reported that they do a lot of manual fine-tuning for timing of their signals as well. And this was an interesting finding, showing that although other softwares that were very well known and very well respected in the past, like Transit 7F, Passero, Max Band, were used years ago very heavily, are no longer the models of choice in the Southeast. And this gives us a hint that you know, agencies are willing to adapt and change. And this is definitely, you know, something that is interesting to know as we move forward and new options become available. The survey participants were also asked to report on their use of simulation or computational models in support of signal control optimization and management. And based on their answers, we found that sim traffic is the most used simulation model by survey participants of different size agencies. And we also solicited some information regarding the types and sources of data that they currently use to evaluate signal performance. And as you can see from the results documented in Table 10, agencies that were surveyed use a variety of data types for evaluating signal performance, with intersection crash data and outputs from simulation models, including the HCS, being the most relevant data types used. When asked about the use of new types of data, emerging data collection, the majority of the large agencies, as well as mid-sized agencies, reported that these are being considered for future use. But interestingly, the small agencies did not show any interest in using new types of data sources, or perhaps were not familiar with those data sources yet. Moreover, large agencies reported being much more interested in investing resources toward emerging technologies in the future, and the same with medium-sized agencies. These emerging technologies for signal optimization include high-resolution controller data and connected vehicle data and the such. We also asked agencies about resources, just to get some idea about their barriers, maybe for performing their work. And so the majority of agencies surveyed feel that they have limited resources with respect to technical staff, budget, software, data, and training, as you can see on the screen. And additional resources will be needed in order to adequately meet the future needs. So 2/3 of the agencies reported that. And so we pressed them on a little bit more to gain a more in-depth understanding about what are these resources and how they would prioritize them. And when we asked them to prioritize their needs, funding, staffing, and software were the top priorities. And this was consistent among the agencies that we surveyed. And it is also consistent with earlier studies that, again, from nationwide surveys that reported resource limitations related to funding and staff as being the most significant factors contributing to suboptimal signal retiming and optimization. So in conclusion, the survey of practice that we performed in this study confirmed that large size agencies have much more interest and opportunity to invest resources toward emerging technologies and techniques for signal optimization compared to small size agencies in the Southeast. But the majority of agencies feel that they have still limited resources with respect to staff and budget, and in order to properly handle signal optimization and management needs. What was good about this survey was that it was the first survey in the Southeast that documented those agencies' practices, and having information from a variety of agencies of different sizes that manage almost 10,000 signals provide some good background information on what the current practices are, where the opportunities are for improvements, and what the current barriers are. And so we hope that this survey will provide some useful information to others that have an interest in this field and will assist them in improving signal timing optimization and management in the future. It definitely informed our next part of the work, where we used some inputs from this survey to develop methods for selecting signal timing parameters using data from multiple sources and modeling. And with this, I will turn the microphone then and stop the share here. And Dr. Hadi will discuss this part of the work next.
Thank you, Virginia. Trying to maximize. Okay, thank you, Virginia. As Virginia said, I'm going to talk about the second part of this project, which is some methods that we developed for selecting signal timing parameter using data combined with modeling. I want to acknowledge two of our researchers, Ms. Tahneen Tariq, now Dr. Tahneen Tariq, who graduated with her PhD, and Rajib Saha, also Dr. Rajib Saha now. Both of them graduated recently, but they worked on this project with us, with Virginia and myself. But I'm going to talk about, again, is examining the data from multiple sources combined with modeling to identify the needs to switch to special signal timing plans during incidents and develop methods to generate those special signal plans and identify the impacts of the activation of the special signal plan during both freeway incidents and arterial incidents. We have done also, as part of this project, some work on using the data to calibrate macroscopic and microscopic models during the, that you are used in the optimization. But because of the time limit, I'm not going to talk about that part of the project. It is in the final reports. I'm going to focus on special signal timing plans during non-recurrent congestion incident and surge in demands and on the freeway and arterials. So we're going to start with the development of signal timing plan for arterial incident conditions. When we have a lane blockage that impact the capacity on the intersection. There are different type of data that we used and can be used. The operator log is something that I'm going to talk about how we use that, where the agencies in South Florida, they have some operators that have a lot of experience in traffic operation. They look at the traffic and they change the signal timing plans based on the traffic. So we got this data. There are also point detectors, Bluetooth readers, and Wi-Fi readers, and private sector data from third party that give us travel time in this case. High resolution control data, as Virginia said, becomes widely used by agencies, and we use some of the parameters from there: turning movement counts, actuated phase timing, green occupancy ratio, split utilization ratio, and percentage of arrival on green. That these parameters were used. We use also connected vehicle data to in some of our work to determine the diversion routes and also during freeway incident, and also to determine the queues, because which movement is the movement that is impacted most by the diversion, because as we know that the high resolution controller data give us data that are close to the stop line and doesn't give us the queue backup to the upstream intersection. We don't know the percentage of those that are going left versus the through. So we use that connected vehicle data to supplement the high resolution control data in that aspect. But mainly high resolution control data and is the one that we widely use. So one of the first thing that we did was to take the data, the log file that I mentioned that are used in the traffic management center, and we tried to replicate the expert decisions using decision tree and fuzzy logic. So without even optimizing the signal timing, we said, what if we take the decisions that the operator did based on observing the traffic condition using CCTV cameras on arterials and making the decision. However, that is obviously is somewhat effective, but first of all, it is time consuming. Sometimes it takes, the operator has to wait until the event happen and the impact happen and then make the changes. It is not available 24/7 because the operator only work on the peak hours, and it depends on the expert. If the expert leave their position, then that knowledge is lost, and then also there is no guarantee of optimization. What we have done then is to do two things or two alternatives for selecting a signal timing plan. The first alternative is to emulate the decisions that are made by the operator using decision tree and fuzzy logic. And the second alternative is to use actual optimization, simulation-based optimization during incident conditions. So if we look at the first on the arterial incident methodology, we first automate the expert decision using machine learning, and we also use high resolution controller data to partition the traffic conditions based on field data. And then we put them into a model that is calibrated in VSIM, calibrated and validated, and any micro simulation model you could use for this purpose. And then we did signal timing optimization for the non-recurrent optimization and testing methodology. And then we can compare the two methods, the optimization-based method and the machine learning-based method, to see which one produces a more effective solution. When we talk about the expert decisions to change signal timing, some of the parameters that are utilized by the expert as they watch the cameras, they recorded those in their databases. That's why we were able to use these parameters in the machine learning process. So they record the queue length, how important is the upstream intersection. So they have a judgment call on the intersection. If it gets blocked, how bad that blockage will be. How much is the increase in demand, if there's surge in demand, how much they feel percentage-wise, and based on data, or based on if there are no data to supplement that, they put a number based on their estimate. And then capacity reduction ratio to say how much is the capacity has been reduced, and then time of day. And the operators there are, like there is master and PhD in, believe it or not, they have master or PhD in transportation engineering, but they were working with the operators to make these, to produce these data. So this is a description of this process. We develop a decision tree, and then we use the methodology to convert the decision tree results to a fuzzy logic, fuzzy logic rules, and produce that fuzzy logic, and then we use that fuzzy logic based system in making decisions. So this is decision tree based on expert decision, and you can see that the queue length, the demand increment came up to be significant, upstream intersection important. So basically those are the decision about how by how much is the operator going to change the signal timing, and when they're going to change it, under what conditions. So that's the decision tree. Then consider those factor, capacity reduction, and so on. And then we took these results and we converted into a fuzzy logic. So if we're going to encounter this situation in the field, then we could run a simple tool, and we developed very simple tool for traffic management centers to be used. It could be improved in terms of user interface, but it does the job. You put, okay, the start time is this, queue length is this, upstream intersection is this. We already run an offline the log, and we produce decision tree and fuzzy logic for those locations. And now we are able to just make the decision ahead of time, a lot of times, and then even if that expert, which in fact couple of the experts that were working in that location, at least one of them I know left their position. So now we could, the people that follow could use the same knowledge that the other expert using this tool. So as I mentioned, the first thing was to develop this machine learning approach that combined decision tree and fuzzy logic, and then we wanted to compare that with an simulation-based optimization. So what we started with, the process is we coded the network. We did multi-scenario based simulation, and optimization. So what we did is use cluster analysis of the data from multiple sources, including travel time data and high resolution controller data. And we cluster them into different conditions. And then we calibrate the microscopic simulation parameters using multi-objective genetic algorithm-based algorithm called NSGA2. What we try is, the objective function is the difference between the field and simulation microscopic parameters. And again, we look at the high resolution control data in the field and travel time in the field and volume in the field, and compare it to the simulation parameter corresponding simulation parameters. So what we, in the optimization objective function, we had travel time, we had the throughput for the movement, and we had split utilization ratio. And then we calibrate the process using this genetic algorithm approach, the SGA, NCSGA, and we obtain the results, and you can see that the calibration results improve the result of the difference in terms of travel time and in terms of the utilization ratio for all movements, for most movements that we work on. And then we also, when we look at the difference in the green occupancy ratio and percentage of arrival on green, that also improved by using this simulation calibration process that include additional parameters other than just the travel time process. once we calibrate the simulation model in this way, we use that simulation model. We produce an optimization signal timing optimization algorithm that is integrated within the simulation model. And we use the calibrated simulation model for different scenarios, different incident and traffic scenarios, and in that optimization process. So the optimization then here include corridor travel time and the critical direction, which is the incident direction, intersection delay, because we didn't want to, obviously we don't want to bias the optimization toward one direction and affect everybody else on the intersection. So that is another parameter, variable in the optimization, and the average throughput of all movements. And the optimization that we used include, we come up with different signal timing optimization for one-lane blockage events under different condition, two-lane blockage events under different condition, and demand surge that happen. And then that optimization allow us to come up to find the Pareto front of solutions that compromise solution for all objectives that the analyst can, or the person that is doing the optimization can select from that balance the throughput versus the delay versus the travel time. And then what this slide show is that there is a lot of there is improvement in intersection delay, corridor travel time, throughput, and queue length, and between the without optimization, during the incident, if we use regular timing, which is the dark green, I guess, or and then that is produce the highest delay and so on, the worst performance. And then the gray, the light gray, is with using the decision tree and the fuzzy logic based on the operator decisions. And the third one, which is the black, is the optimization using simulation-based optimization of the signal timing during incident conditions and demand surge. And the optimization produce the best results, but obviously it is the more time consuming than doing the machine learning. If you have the right data for machine learning, you could also possibly produce better results than this. And but considering that the data that we have. Considering the data that we have, this is the results that we got. The second part, which I'm going to go fast because again, it doesn't. I didn't want to take long time to explain, but it is included in the final report. Part of also there's additional information about this as part of an FDOT project for the Department of Transportation project. So there were matching projects, and we did part of the work in this STRIDE UTC project and part of the work as part of the FDOT project. So the two reports complement each other somehow when it comes to the freeway incidents. For the arterial incidents, all the work were done as part of this project. But in general, with the freeway incident, what we tried to do, or what we did, is we use machine learning to identify what are the alternative routes that are used under different incident conditions. And then again, use machine learning combined with modeling to determine the alternative route utilization, what is the percentage of vehicles selecting different route. And then we develop a method for selecting and activating special signal timing plan. So again, I'm not going to talk about the details of that a lot, but we have done some neural network work and to determine LSTM neural network and to determine what alternative routes are impacted based on the increase in travel time during various incidents on the freeway. We determine also some changes in the demands that occurred during those incidents, and then we also recognizing that we don't have all the incident conditions in the network. We calibrated a multi-resolution model, a multi-resolution model to estimate the diversion under situations that we have not seen in the real world, but we calibrated for situation that we saw, like one lane blockage at 4 o'clock. We calibrate the model to produce the same diversion during that incident. Then we extend that to situation that may be in a different hour of the day or other conditions that we have not seen in the data to produce additional scenarios using multi-resolution modeling. So, and at the end, what we have done is then again did the optimization of the signal timing using the simulation-based optimization that I spoke about before, where we optimize the signal control using optimization NSGA and model integrated within the micro simulation. So again, we use machine learning and clustering analysis for the prediction of alternative routes. We use multi-resolution modeling combined with data analytics for estimation of traffic demands on alternative routes. And we use simulation-based multi-objective optimization. So I'm going to just show to give more time for questions and answers. I'm going to just show the results, and you can see for different scenarios that we modeled, different incident scenarios here with different clustering. We did different clustering on these scenarios, cluster analysis. And you can see that there is a reduction. And again, these are for the freeway incidents and with application of the signal timing on the arterial. You can see that there is a reduction overall delay and delay on the diversion routes themselves, which is even more percentage-wise is higher, obviously, because the other one look at the overall delay on the arterial network. Increase in total throughput and increase throughput on the diversion route. And then in summary, this combination of data with machine learning and optimization and simulation can produce effective way of selecting developing signal timing plan and provide recommendation for the activation of the signal timing plan. And when we look at the decision tree and fuzzy logic model and the optimization model, we can see that they are effective. The optimization is even more effective if the model is well calibrated than the decision tree. However, obviously, if the decision tree has better data, then we expect that performance to be much more improved. And so we again this is also the case for the diversion during incident, freeway incident, the selection of signal timing plan based on these components, which are the machine learning, multi-resolution modeling, optimization, simulation, can produce effective signal timing plan. So this ends my presentation. There is a link that very brief survey. So we appreciate it if you click on the link and provide the answers. It's very brief. And as Virginia said, please enter your questions in the chat box, and we will be happy to answer this. Before we do that, I just want to mention that there are two upcoming webinars. One is on May 26th, demonstration study of older driver experiences with autonomous vehicles. And on June 16, transportation to healthcare and COVID-19, exploring pandemic era travel trends and post-pandemic challenges and opportunities. Thank you. So there is, I see, do you, Virginia, do you want to read the questions?
Yeah, sure, I'll be happy to do that. Let me just, we have one question that reads from a participant that comes from Kurdistan, Iraq. And they ask, we used HCS 9.2, but faced some difficulties in entering data for existing situation, as each approach has one phase and each phase is moving separately. Do you have any idea about the software and solution for this case, or do you have any solutions or software that you can recommend? And you do have this also on the chat box, Mohammed. It is for you if you'd like to take a look. So they have used HCS 9.2 and they are wondering if there are any better methods.
Yes, so thank you. Obviously, I'm originally from Iraq. I've been to Arterial a long time ago. Mm-hmm. And thank you for the question. Obviously these softwares, some of I am not sure about the question about the HCS. I don't understand it fully, but these softwares have limitations. So they a lot of time you reach that limitation and you cannot go beyond it. And when you have that, then you have to go to more to different tools that go and provide what's needed, and that's why you have simulation analysis, for example, and maybe other optimization software that you can use, because in reality the HCS is not the main objective of the high capacity software is not optimization. The main objective of the high capacity software is the analysis of the movement, and a byproduct is the optimization. So look at other tools and you will possibly find one that works for you. With regard to the simulation-based optimization, yes, it was written in API. We wrote it, not very user-friendly because it's not like commercialized version of it, but we wrote it for, it's a research version, I would say, of that. So yes, we wrote that.
Thank you for this answer. And we have one more for you, Mohammed. It reads as follows: was the simulation-based optimization a feature of the software, or was it a custom module implemented through an AP, that is the application programming interface?
Yeah, and that's the same. Yeah. I just answered that. Is yes, we wrote it in API, and we wrote our own code to work with the software.
All right, very good. So let me just turn my video back on, and I would like to take a moment to thank everybody for attending today. We really appreciate it. I'm sure that Stride will share also a link to this presentation. So if you have any additional questions or any comments and suggestions, feel free to reach out to us at any moment. So unless Odin would like to share any other announcements, I would just encourage you to take that one moment to give us feedback through the brief online survey. With that, I think we will be ready to wrap up for today. I would like to thank everybody and wish you well. Have a great day.
Thank you.